Hello guys, in this video we are going to discuss colligative properties. But before that, I would like to tell that I'm also on Patreon, where you can find additional content about chemistry, and also I'm building my course about organic chemistry lab techniques, which can help you for your PhD or your thesis work. So what are colligative properties? First of all, the name colligative properties comes from the Latin word colligo. Colligo stands for to bind together. So as you can find in all the textbooks, colligative properties would mean properties which depend on particles as a whole and not depend on the chemical identity of these particles. However, I didn't find this explanation so clear. So I went back to my old Latin dictionary and I found out that colligo means also to count. So if you connect the word colligo to the word to count, it will be easier for you to remember the concept. Because colligative properties are properties who depend on the number of particles, but they do not depend on the chemical identity of those particles. So they can be whatever. That's the reason why I put in the title that this time you can count pears with apples. No one will tell you that is wrong. But be ready to tell to your professor the first etymology I told you, because the first etymology is written in all the textbooks, so we don't want to bother our professors with new explanation, okay? We want to pass the exam. Remember that. So, what are these colligative properties? In particular, colligative property refers to how some properties of the solvents are changed when we put a solute inside the same solvent. As we have already said, colligative properties do not depend on the identity of the solute we put in the solvent. So they do not depend on the identity of this solute, but they depend on the amount of solute we put inside. So they depend on the number of particles of solute which are dissolved in the solvent, and indeed they depend on the moles of solute we put in our solvent. We have in total 4 colligative properties: lowering of the vapor pressure, elevation of the boiling point, depression in freezing point, and osmotic pressure. Before going into that, let's see a generic formula can help us to understand all the equations we will see throughout this video. The basic equation for all colligative properties is the simplest math equation we have in math, which is direct proportion. As you may know, the relationship of direct proportion is y equals c times x. C is a constant. If x increases, y will increase proportionally. So this is also the equation we have to consider for our colligative properties. However, we have to make it more specific. So instead of y, we have to write delta. Delta always stands for a difference between two values in math. And x will be our concentration. So we can write it with the letter C. Therefore, the equation can be written again in this manner. Delta equals K, which is our constant, times C, which stands for concentration. So delta is our variation of colligative properties which are going to happen in our solvent when we put inside a solute. And C will be our concentration. K our constant. But why I wrote C with apostrophe? Because for each colligative properties we are going to discuss, C will be different. So the way to express concentration will be different. For example, C will be mole fraction for lowering of the vapor pressure. C will be molality for depression of freezing point and for elevation of boiling point. And C will be molarity for osmotic pressure. However, this generic equation can be actually modified based on what type of solution we have. In particular, if we have non-electrolyte solution, the equation will stay the same. Just to quickly remind you what a non-electrolyte solution is. Non-electrolyte solution is a solution which the solute is not dissociated in ions. For more details, you can watch my previous video about solutions and concentration. But just to clarify, non-electrolyte solution is, for instance, water plus sucrose. Okay? So, non-electrolyte solution, no ions. But what happens if you have a strong electrolyte solution? Strong electrolyte solution is a solution in which the solute will be dissociated in ions. For example, kitchen salt. Kitchen salt in water is dissociated in Na+, so sodium cation, and Cl-, so chloride anion. This is a strong electrolyte. So this is a strong electrolyte solution because all the NaCl will be dissociated in Na+ and Cl- with no NaCl left. For strong electrolyte solution, we will introduce a coefficient which is called Van 't Hoff coefficient in our equation. This Van 't Hoff coefficient is indicated with the Greek letter Ni. Ni refers to the number of solid particles will be formed in solution. Let's be back to our sodium chloride just to show you an example. Sodium chloride, as we have said, is dissociated in water in Na+ and Cl-. For 1 mole of NaCl, you will form 1 mole of Na+ and 1 mole of Cl-. If you do 1 plus 1, it's of course 2. And so our Ni, it will be 2. Why? Because for 1 mole of NaCl, now in solution I have 2 moles of particles. One is Na+ and one is Cl-. Okay, so you have to sum the coefficient you have in your equation. Let's try with another salt, for example, calcium chloride. Calcium chloride is completely dissociated in water in Ca2+ plus 2Cl-. Now, if you sum the coefficient, you will have coefficient 1 for Ca2+ and coefficient 2 for Cl-. So 2 plus 1 is 3. So this time Ni is 3. This is the coefficient we have to add in our equation for colligative properties. But what happens if you have a weak electrolyte solution? First of all, weak electrolyte solution is, for example, acetic acid. Acetic acid in water is dissociated in CH3CO- plus H+. However, this is a weak acid, so acetic acid is not completely dissolved in these 2 ions, but you will have also acetic acid undissociated in water. So this is the dissociation of acetic acid in water is not complete. So how to calculate colligative property for weak electrolyte as, for instance, acetic acid? This time the equation will be slightly complicated because we have to introduce alpha, the Greek letter alpha, which is the ratio between dissociated moles of our solute, for example, dissociated mole of acetic acid, divided by the initial moles. So the equation will be delta equals K times C, bracket square 1 plus alpha, parenthesis, Ni minus 1. So you need to know this alpha in order to resolve this equation. Be careful because these three equations we have seen are valid only for dilute solution. Why? Because in the case of highly concentrated solution, some phenomena, for example, association of ions, will change the real concentration we have there. Okay? Let's do an example. If we put an excess of NaCl in our water, some sodium cations will tend to associate with some chloride anions as plus-minus attraction. In this case, the actual concentration we have in solution will be less than the ideal one. In the case of highly concentrated solution, we have to add a coefficient again for all these three equations we have seen, which is another Greek letter, which is the letter phi. Phi stands for activity coefficient. If phi is 1, it means that we do not have these association events, so our three equations will be those we have seen at the beginning. If phi is less than 1, this means that the variation of our colligative properties are less than expected because of those association events between ions. Now, what is the use of these colligative properties? First of all, colligative properties have many of application in the real life. I will do a small video about that and I will link it into the description below as soon as we'll be ready. But there are also some application in chemistry. This application in chemistry is obsolete. However, in the past, colligative properties were widely used for the calculation of molar mass of the solid. Indeed, with a simple rearrangement of the general equation we have just seen, you can calculate the molar mass of your solid. So just by recording the difference of colligative property, you can calculate the molar mass of your solid. These calculations were done in the past mainly using depression of freezing point and elevation of boiling point. For solids with very big molecular weight, for example, polymers and proteins, the osmotic pressure was the main choice for this measurement. Nowadays, there are new techniques for the calculation of molecular weight, which is mass spectrometry. So the use of colligative property for the calculation of molecular mass is outdated. However, if you do not have a mass spectrometry at all, now you know you can use colligative properties for the calculation of molecular mass of your solid. Now, let's go to see these properties one by one. The first we are going to see is the lowering of vapor pressure. What is vapor pressure? The vapor pressure is pressure of a gas which is in equilibrium with its liquid. What does it mean? If you take a liquid and put it in an open container, some of the liquid will tend to evaporate. And by the time, since the container is open, the level of liquid will decrease. And after some time, all the liquid will be gone. The speed of this process depends on the volatility of your liquid. For example, toluene can take some months before it will be all gone. On the other hand, liquids as dichloromethane or ethyl ether will take a bunch of minutes. However, if you seal your container, some of the liquid will anyway tend to evaporate. However, since this time the container is closed, some of the vapors will again return into the liquid phase and become again liquid. When the rate of evaporation equals the rate of condensation, an equilibrium will take place between these two phases. The pressure of the vapors, which is in equilibrium with the liquid, is called vapor pressure. Now, what happens if we add a solid in our pure solvent? This vapor pressure decreases. Let's do an example. If I have pure water, the vapor pressure of pure water at T1 temperature, can be room temperature, whatever, will be P1. Now, if at the same temperature, T1, I add a solid, for example, sodium chloride, inside this water, what will happen? Will happen that our vapor pressure will be different, will be P2, and P2 will be less than P1. This means that this time we will have less particles of water in the vapor phase. The guy who studied this phenomenon was Raoul. Raoul was studying mixture of liquids, okay? One day he found out that if you have two miscible liquids, let's say A and B, mix it together, the total vapor pressure of these two liquids will be given by the following equation. So the total vapor pressure of these two liquids will be given by the vapor pressure of the liquid A times the mole fraction of the liquid A in this solution plus the vapor pressure of B times the mole fraction of B in this solution. Be careful because this mole fraction refer to the mole fraction of both solvents in the liquids, okay? It's not referred to the mole fraction in the vapor phase, okay? But just in the liquids. Now, this equation that looks like far away from our topic actually is related to our colligative property of lowering of vapor pressure, because if we consider B not as a liquid but as a solid, and we consider this solid to be not volatile, what will happen? Will happen that we are again back to our example of water plus, for example, sodium chloride. Sodium chloride is a not volatile solvent, so we are considering our problem of lowering of the vapor pressure. And what will happen to our Raoult equation? It will happen that the second part of the equation will be cancelled, because the vapor pressure of the solid B, since the solid B is not volatile, will be 0. So the vapor pressure of B is 0. This means that all the second part of the equation will be cancelled. So what we have left? We have left that the total vapor pressure equals P0A times XA. Now, what is this total pressure? The total pressure will be actually the pressure of our solution. So we can write, instead of P total, we can write P solution. So P solution equals P0A times XA. That if we go back to our example, this will be the vapor pressure of water and the mole fraction of water inside the solution. Now, since mole fraction are fraction in months, you can write the mole fraction of A as equals to 1 minus the mole fraction of B. So B is the mole fraction of the solid. In the case of our example, it will be the mole fraction of NaCl in the solution. So now we will have this new equation. If we multiply P0A with what is wrapped in the parentheses, we will gain this new equation. After a rearrangement and a sign change, we get that the difference between the vapor pressure of the pure solvent A and the vapor pressure of our solution equals P0A times XB. If we call this difference delta, we are back to our basic equation I gave you at the beginning of this video. Like the general equation, also this one will be split in 3 different equations according to the solution we have. So, non-electrolyte solution, strong electrolyte solution, and finally weak electrolyte solution. But let's try to understand why the vapor pressure of a pure solvent is decreased when we add a solute inside. This happens because the solid particles will interfere with the solvent particles which are trying to evaporate. Because the solid particles will interfere with the solvent particles such a way that the solvent particles will be hindered by the solid particles in their evaporation process. So this will affect the rate of evaporation, which will be lower. That's the reason why the vapor pressure will decrease, because now there will be less particles of solvent in the gas phase. This is a childish explanation, but it's enough for our level. In physical chemistry, the explanation of this phenomenon will include the concept of chemical potential, but this is too advanced for now. As I have told you at the beginning of this video, colligative properties were used to calculate the molecular weight of the solid. So if you rearrange your equation for the lowering of vapor pressure, you can have the molecular weight of your solid. Now, how to gain this new equation, I will write in my Patreon channel, you can check it, but the basic concept is to make the mole fraction as the subject of the equation and write mole of solid as mass of solid divided by the molecular weight of the solid. Then there are other mathematical steps to gain this final equation here. Now, let's move to the elevation of boiling point. The elevation of boiling point means the increase of boiling point for a solution if compared with the pure solvent. I would like to remind you that boiling temperature is the temperature when the vapor pressure of the liquid equals the atmospheric pressure. When this happens, the liquid has enough strength to win the atmospheric pressure that otherwise press the liquid to stay down. Now all the liquids can vigorously evaporate. Now the boiling point for pure water is 100 Celsius degree. But if we add a solid, again let's take the kitchen salt. We don't have fantasy today. Let's take the kitchen salt. We already know that the vapor pressure of water will be decreased. It's our first colligative property we have seen. So now the vapor pressure of the water will be less than the vapor pressure of pure water. The elevation of boiling point is a consequence of the lowering of vapor pressure. So our flask with NaCl and water, if we warm it up at 100 degrees, now at 100 degrees the vapor pressure will be lower. So this means that the vapor pressure is less than 1 atmosphere at 100 degrees. So it's less than the atmospheric pressure. So to compensate that, we need now to increase the heat to reach the atmospheric pressure. So we need higher temperature for reaching the boiling point. So what is the equation for elevation of boiling point? The mathematical law for that is very similar to the generic equation. So we can write delta for the boiling point equals K times M, where K are value you can easily find online or your textbook, and you can find them for each solvent. And M is molality. Just to remind you, molality is the concentration expressed as mole of solid divided by the mass of solvent in kilograms. So how these constants were calculated? It's very simple. They were experimentally calculated just by taking solution with molality equals to 1. Because if you have molality equals to 1, you will have that the equation will be only the variation of boiling point equals the value K. So you can know K. Be careful now, because this delta is not the same as we have seen for the lowering of vapor pressure, because delta this time is the difference between the temperature of the boiling point of solution minus the boiling point of the pure solvent. As you can see, these values are put now in the opposite direction if compared with the lowering of vapor pressure, when delta was the difference between the vapor pressure of solvents minus the vapor pressure of solution. This is because now we are considering an increase of something, and the delta value has always to be greater than 0. So you have to put those terms, the property of the solvent and the property of solution, in the right order in order to have this delta value all the time greater than 0. This is the reason why you have to a little bit think if you are talking about an increase in some property or a lowering of some property. Okay? Now, very similar to the elevation of boiling point is the depression of freezing point. This property refers to a solvent which is freezing in a solution. The presence of solute particles prevents the solvent particles to reach the lattice. So the crystallization rate of the solvent in a solution is lower than the rate of pure solvent. This means that now I need lower temperatures to allow the solvent to crystallize if compared with the temperature of pure solvent. So basically, if we have pure solvent and we have the same solvent in solution, now the temperature of crystallization of the pure solvent is greater than the temperature of the crystallization of the same solvent in solution. So what will be the equation this time? The equation is pretty similar to that one of elevation of boiling points. Namely, we will have delta for the depression of freezing point equals K times, again, molality. Again, K are tabulated values you can again find in your textbooks or online. What delta means this time? Since we are talking about again a depression, so again a lowering, this time the value of delta will be pretty similar to the lowering of vapor pressure. So it will be the difference between the temperature for crystallization of the solvent minus the temperature for crystallization of the solution. Because the temperature for crystallization of the solvent is greater than the temperature of crystallization of the solution. That's the reason why you have to put in this order, because you have always to have delta greater than 0. That's the reason why, again. Again, as for the lowering of vapor pressure, also for the elevation of boiling point and for the depression of freezing point, you can find an equation to calculate the molar mass of your solute, which is this time this one. And you can get it if you write mol as the ratio between mass and molar mass inside the definition of molality for both of these two colligative properties. Let's move now to the last colligative properties, which is osmotic pressure. The property of osmotic pressure is similar to the phenomenon of diffusion of gases. Diffusion is a movement of a substance from an area of high concentration to an area of low concentration. The same principle happens for liquids. Let's take a pure solvent in touch through a semi-permeable membrane with a solution. The semi-permeable membrane is a membrane that lets only the solvent to pass through this membrane. So it is selective only for the solvent, because this membrane has some pores which have the right size to let only the solvent particles to pass through. Now, what will happen if we have this situation? Solvent, solution and semi-permeable membrane in between. What will happen is that a difference in height will be formed between these two solutions. This is because the pure solvent will pass through the membrane and will go into the solution. This is happening because inside the solution there is less solvent, because solution has also solute inside. So the concentration of solvent inside the solution is less if compared with the concentration of the pure solvent, of course. That's the reason why the solvent is going inside the solution. It's the same principle of gaseous diffusion. Now, the pressure we have to give to the system in order to stop the formation of this difference in height is called osmotic pressure. The equation for osmotic pressure comes from the ideal gas law. The ideal gas law, I want to remind you, is PV equals nRT. If instead of generic pressure we take into account the osmotic pressure and we put the volume in the second part of the equation, we will gain this new equation. If we mark the osmotic pressure with the letter Greek P, we have this one. Now, if we consider that N over V is molarity, we can write the final equation for osmotic pressure, which is P equals molarity times RT. This is anyway fitting with our general equation we have seen at the beginning of this video, because RT is our constant and N is our concentration. Now, what happens if instead of solvent and solution we have two different solutions? The solutes in these two solutions can even be different. The only thing is that the solvent should be the same. So what happens in this situation where we have two solutions separated by the semi-permeable membrane, and these two solutions have different concentration? The osmotic pressure this time will be given as difference between the osmotic pressure of the two solutions, and this will be equals to the difference of the concentration in molarity of the two solutions times RT. Now, as you can see, if the two solutions have the same osmotic pressure and they have the same Ni, the Van 't Hoff coefficient, these two solutions will have the same concentration, and they are called isotonic solution. So this was the last information. I hope you enjoyed this video. Let's write me down in the comments if it was helpful, and we will see in the next video.